Good afternoon. I'm here with Tom Campbell, author of My Big Toe, A Big Theory of Everything, and designer of several variations of the classic double-slit experiment that he hopes will produce evidence of the nature of our reality. Tom's guests are part of his valuable research team for the experiments. Tom, if you would like to introduce your guests and discuss between yourselves the current status of the experiments, or your experiment backers and audience, I'm sure it will be gratefully received. Tom?
Okay, well, first of all, what Donna has come into here is a weekly meeting that the research team has, every Thursday afternoon. And, we do this to keep up with what's going on, what the problems are, what we're doing to solve those problems, and so on. So Donna asked if she could jump into our meeting in the beginning and get a little update from the research team. So that's what we're going to do. Okay, down on my bottom left is Farbad Kashnud. He is the main researcher. He's the guy doing the work. He's getting the equipment, buying the equipment, putting it together, and trying to make it all work. And we've been doing this now for some months. Every week we get just a little bit closer. New equipment gets bought, new ideas to how to test it, and we make progress. Very slowly, but progress just the same. Now, just below me is David Chartrand. David is part of this research group. In fact, he came up with a little version of the double slit experiment that seems to be easy and cheap. But now let me put easy and cheap in quote marks, because it hasn't actually been easy or cheap so far, but it seemed to be easier and cheaper than the other ones we had. We just needed a solid standard double slit experiment, such that there was a separate path for the which way data. That was the key idea. There's lots of ways of doing a double slit experiment, but they all don't end up with a unique which way data path that you can erase or not erase. And since we needed that, David came up with a simple one that is working with entangled photons and polarizers, and it looks like it will work, but we're struggling at the moment to put it all together, but everything looks good. So I'm going to let Farbad and David say a few words, if you will, just to let the people know of sort of what we do here and where you think it's going, Farbad. And I know what everybody wants to know is, when were there going to be results? When are you going to have results? That's the big one. So I know that's probably impossible for us to say at this point, because we're just in the problem solving phase, putting it together, and some problems are easier and quicker to solve than others. And these haven't shown themselves to be real easy or quick. So we actually don't know exactly when, but go ahead, Farbad.
Okay, thank you. Thank you, Tom. So behind me, we have the experimental setup. At the moment at California State Polytechnic University, Pomona. So Tom already introduced me. So my name is Farbad Khoshnud. I'm a faculty member here. So we have been trying this experiment, as Tom mentioned, is a combination of quantum entanglement, photon quantum entanglement, and double slit experiment. So I've been trying this experiment and setting up the alignment. So for you, for the people who are watching this video and have experience with double slit photon experiment, they know that this is kind of an optics experiment originally, and then we are going to try to measure or count the photons one by one, so single photon counting. We have some sensors at the back that is doing the single photon counting, and then the process of that quantum entanglement part is what is called down conversion experiment. Okay, so And then the entanglement, basically the photons that are entangled using a BBO crystal that we are using, one going to one sensor, and then the other one going to double slit, and then the double slit sends it to other sensors. And so far, the sensors that we have, the experimental setup we have, the results that we are getting is not as good as we expecting. So that's one reason, is because of the sensors are not strong enough, powerful enough to count the single photons and detect the photons that we are expecting for the entanglement. So now we are getting a new, more popular type of photon counting module, which is from Excelitas. The brand is Excelitas is the name. And we're going to do a new setup here, and then repeat the experiment, and then collect data and see what we get. So we have been trying this for a few months, or actually from last year, since last year, we have been trying this. And we are learning more and more every time we do experiments, and we are hoping to get some results soon. So if we get the result that we are expecting with the new sensors, which we are expecting to receive maybe next month or late this month or early next month, then who knows, maybe we get the result next month. Maybe we get the result that we are expecting. But the past experience shows that it's not as easy or straightforward that we expect. So we do the experiment, we collect the data, and then say, okay, maybe that's not as good as what we're expecting. So we need to repeat the experiment. We need to get different type of maybe equipment. So we keep repeating the experiment, keep getting new equipment. Every time we get a new equipment, we go through a long process of months of getting a new equipment. So that delays our work significantly, but we never stop. We keep working, we keep experimenting, we keep changing the setup, and we keep learning, studying. And so is a matter of basically when, but we will get a result. We will get a result. So we know that we will get a result. It's just a matter of when we are getting that result that we say that this is meaningful enough for us to publish it, to publish. Thank you.
Hey, David, looks like you have some graphics for us to look at.
Yeah. Thank you, Tom. I'm more on the theoretical side of things. We started with Tom's ideas of the experiments, the 5 experiments, and I tried to make a setup that was simpler and cheaper, but still really hard to do. So maybe I can show one very quickly, which is the one we aim to perform. I cannot share my screen right now. If you give me access, I'll do it.
All right, I surely will.
But in the meantime, I just want to say that one of the big challenge for people out there that are not really used to do optic experiments is that there are billions, if not trillions of photons all the time, all around us. And we are trying to do an experiment where we send one single photon at a time through a setup and then detect that photon, but also detect its entangled pair at the same time. So here we're talking about nanosecond scales and just detecting one photon out of trillions of photons all around us. So it's really hard. Even in a totally black room, we still get hundreds of photons per second on the detector. So it's really hard, but we're moving forward. So now if I share my screen, so I will just explain very quickly the experiment we are trying to do. So here we have the laser source. So this sends a bunch of photons through a laser. It gets to a BBO crystal, and the BBO crystal, through a spontaneous parametric down conversion, creates a pair of 2 entangled photons. So one of the photon goes in the upper path, and the other one goes to the bottom path. And these 2 photons are entangled in the sense that they share information about each other. And the idea is that when the bottom photon will get to the double slit, the other photon will know by which slit its twin went through. So it's how we detect the which way information. So if we follow the bottom photon, it goes through the bottom path, then goes through slit A or slit B. We don't know, but it will go through either of the slits. And then we put polarizers in front of the slit. And the reason why we put polarizers is that, without going too much into the details, is that these photons are entangled by polarization. So if the photon was able to go through the upper slit, through the horizontal polarizer, we know that the upper photon is polarized in the opposite way. So if it's horizontal, the upper one is vertical, and if it's vertical, the upper one is horizontal. So here, this is where we get the which way information. So we know at that point the slit in which the bottom photon went through. And then at the end, the bottom photon goes through a diagonal polarizer, which erases that information. Then we don't know the information anymore. And then the photon hits the screen. And at that point, on that screen, we should get an interference pattern. So an interference pattern because we don't know the which way information. And the idea at the top here, we have a crystal that allows us to know the polarization of the upper photon. If it goes up and goes to detector R2, we know that the upper photon was polarized vertically, so that we know that the bottom photon was polarized horizontally, so it went through slit A. And the opposite is also true. If it goes at the bottom and ends at R1, we know that the bottom photon went to the slit B. And finally, we have a switch that allows us to decide to record the which way data or not record it. So if we turn the switch on, so we raise the little wall here, the absorber, then we will record that information. And if we record that information, then we know it, and then we should not get an interference pattern. And the test here is to say, okay, if we are not recording it, if the information is never available to any conscious observer, do we get an interference pattern at the bottom? So in a nutshell, that's the experiment. I won't go too much into details, maybe in the future, but it gives you a feeling of what Farbud and Tom are doing every Thursday, trying to get there.
Yes. Such a simple concept theoretically, such a difficult process to actually do in a lab. But anytime you're looking at particles that are traveling the speed of light, you know, it's like 186,000 miles a second. That's fast. And when you're looking at individual particles and then trying to correlate a single one of those particles with, you know, its twin out of all the thousands, if not millions, of particles that are flying around in the system, that is a difficult thing to do. So simple experiment, difficult to get it in the lab working correctly. So that's where we are. As Farbod said, with really, really good luck, it could be as soon as a month or two. But with our experience thus far, that's unlikely. It's probably going to be longer than that because we'll probably run into more difficulties as we go. So far, every step has had its own difficulties, and we have dealt with those, and we're in the process. And as he says, ordering parts takes time. But we're doing all right so far. The budget that we got from the Kickstart program is still pretty solid. We're not real at the end of it yet. We still have money to fund this through to the end, so that looks good. So we will get there sooner or later. I hope it's sooner, but I'll take later. I just want to get it done. And I want to thank Farbod and David both for every week, you know, we have this meeting and we go over the details and we look at charts and we see results and then we decide what to do next. And we've been doing that since the very first of the year. Actually, since a little before the first of the year. I think we started in with this in December. What we were doing before December was trying to narrow down the field and get some of the more upfront work done. And by the last December, we actually had parts and equipment and things to set up. So before that, we were doing the things that are really upfront of that. So that's kind of where we are. Slow but steady. So thank you, Donna, and I appreciate you coming and getting this little blurb for the people at the Kickstarter program. David is one of those. He was one of our star supporters in that program, and anyway, they'll probably be happy to hear what's going on.
Well, thank you, gentlemen, for sharing a little bit of your journey with the experiment today. I'm sure that everyone will be looking forward to seeing this update. It'll be posted on CUSAC on Facebook and on the cusac.org website, and also probably on YouTube. So thank you all very much for sharing this with the experiment's backers and your audience. Thanks a lot, guys.
Thank you.